Let us discuss about the modes of vibration. The modes of vibrations are the modes in which the string fixed at both ends will vibrate. We know from the analytical treatment of the standing waves, lambda is equal to 2L divided by n, where L is the length and n can be 1, 2, 3, 4 dash. For first normal mode, for first normal mode, or it is also called as first harmonic, n is equal to 1. So n is equal to 1 for the first normal mode. In that case, lambda 1 is equal to 2L divided by 1. So lambda 1 will be equal to 2L, or L will be equal to lambda 1 divided by 2. What this means? This means on full length of the string, there will be half the wavelength. On full length, listen closely, pay attention. On full length, there will be half wavelength for the first normal mode. That means if we are having a string attached at these two ends, there will be half wavelength. That means this way. This is a half wavelength. So here at x is equal to 0, there is a node. At x is equal to L, there is a node. At x is equal to L divided by 2. At x is equal to L divided by 2, there is an antinode. It is the first normal mode or first harmonic. Now let us see the frequency of first harmonic. We know that frequency is equal to velocity divided by lambda. So nu1 is equal to v divided by lambda 1. Velocity on a string is root of t divided by m, where t is the tension in the string and m is the mass per unit length. So we can say that nu1 is equal to v, that is root of t divided by m, and 1 by lambda 1. Lambda 1 is equal to L. So the frequency of the first harmonic nu1 is equal to 1 by 2L root of t divided by m. It is the frequency of the first harmonic. For second harmonic or first overtone, n is equal to 2. So here n is equal to 2. That means lambda 2 is equal to twice L divided by 2. 2 goes, lambda 2 is equal to L. That means for the second harmonic or first overtone on a length L, there is a full wavelength. That means when we have got a string tied on both the ends, there will be a full wavelength on that length. That means a wave, standing wave, will look like this. So we are having a node here at x is equal to 0. We are having a node here at x is equal to L divided by 2. We are having a node here at x is equal to L. In between the two nodes, we are having an antinode, and between these two nodes, we are having an antinode. This is the wavelength for the second harmonic or first overtone. Looking for the frequency, we know that frequency for the second overtone will be equal to the velocity divided by wavelength of that overtone, that is v divided by lambda 2. That means nu2 is equal to root of t divided by m, that is the velocity as already discussed. Here lambda 2 is equal to L, that means it is equal to 1 by L t divided by m. We also know that nu1 is equal, for the first harmonic, nu1 is equal to 1 by 2L root of t divided by m. If we look closely, so we can substitute here this equal to nu2 is equal to 2 times 1 by 2L root of t divided by m. 1 by 2L root of t divided by m will be equal to nu1. That means the frequency of the first overtone or second harmonic is 2 times the frequency of first harmonic or first normal mode. Discussing about third normal mode or third harmonic or second overtone, that means here n is equal to 3. N is equal to 3. So the wavelength will be equal to lambda 3 will be equal to 2L divided by 3. Here L is equal to 3 lambda 3 divided by 2. 3 by 2 is equal to 1.5. That means we are having on the length of the L, we are having 1.5 lambdas. That is a full wavelength and a half wavelength. That can be shown if we are having a stretched string. We will be having this shape. The standing wave will look like this. This from here to here, it is lambda. From here to here, it is lambda divided by 2. So we are having nodes at here, x is equal to L. At here, we are having a node. At here, we are having a node. At here, we are having a node. And between the two nodes, we are having a node here, here, and here. Now, let us discuss about the frequency. Frequency of the third harmonic or the second overtone, nu3 will be equal to V divided by lambda 3. So V, as already discussed, is equal to root of T divided by M, and lambda 3 is equal to 2L divided by 3. So that is equal to 2L divided by 3. So nu3 is equal, 3 comes up, 3 divided by 2L root divided by T by M. Giving it the form of how much it is of the first harmonic, we know that for first harmonic the frequency is equal to 1 by 2 L root of T divided by M. So nu3 is equal to 3 into nu1. So the frequency of the second harmonic is 2 times the first harmonic, and the third harmonic is 3 times the first harmonic. We can generalize it as for the nth harmonic. For the nth harmonic, the frequency of the nth harmonic will be equal to n times the frequency of the first harmonic. That is, nu n is equal to n times nu1. Thanks.